Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is network delay time. Let's go to LeetCode and give this problem a read. You are given a network of n nodes labeled from 1 to n. You are also given times a list of travel times as directed edges from basically times I will have the u vertex, which is the source vertex, and then v is the destination vertex, which means there is an edge from u to v, and then the weight of that edge is wi, where this is what I've already said. So we will send a signal from a given node k. K is the source node of this entire graph that we're going to work on, and from there we need to return the minimum time it takes for all the n node to receive the signal. If it is possible for all the n nodes to receive this, if it is impossible for all the n nodes to receive the signal, then return -1. So there might be some node that cannot be reached from the source node. Maybe there is a node like direct or indirect edge that connecting from the source to that node, from k to that particular node, or it's like even not the part of this graph, this whole graph, but like this is disconnected graph. You must have studied in graph theory. Then also we will be returning -1. Okay, so let's get into it. Let's get into it. Okay, so here, as you can see, that I've drawn this first example graph that is a directed graph. These are my vertices, these are my edges, and each edge has an assigned cost to it. Now times is what is basically given to us, and k, and n, the number of nodes. K is the source node, and times is basically this list that has this source vertex, then this destination vertex, from this source vertex to this destination vertex, and this is the cost from u to v. All right, so what we will be doing initially is we will be creating a dictionary that will store, or adjacency list you can say, that will store from this particular source how many neighbors it has. So I can call it like basically you can call it graph or edges or whatever you guys want to call it, but like this will be storing all the edges for a particular node, that all the source node that it has, or the neighbor node that it has, and then also the weight assigned to it. Now let's see what is the problem actually asking us, and how we will be finding this minimum time to basically send the signal from the source node to all these nodes. So in this example, we have the source node as k is equals to 2. 2 is the node that actually sends the signal, and then how much time it's going to take to for all the nodes to receive that signal. So you can see that 2 has a direct edge from 2 to 1, then it will take the time that it's going to take is 1. Then there is another edge from 2 to 3, then the time it's going to take is 1. So now we have reached 1 and 3, and the time that we have taken is 1, because 2 has the possibility of sending the signal at the same time to all its neighbors. All right, so this 1 is basically at the same time it's taking 1 second to transfer that signal to all its neighbors. But we have not sent the signal to all the nodes. There is one more node remaining, which is this, and this also takes one more time. Basically, one comes from weight. This could be different. In this example, they have added 1. They could have made it different. But now this is, so to reach from 2 to 4, the signal is actually taking now 1 plus 1, 2 times, basically 2 seconds. Let's call it second, for the sake of this problem. So 2 seconds. So what is that minimum time that we are going to take to send the signal from the source node to all the nodes? So that will be 2. Okay, that's easy. But what if we make some changes in this problem? Let's say our source node and everything is just common, just we have a little bit of difference. Let's modify this as, let's say 3 had a neighbor, which is, let's call it 4 is taken, so let's call it 5, and the weight of that edge was, let's say 3. Now how our answer will change here? So basically we'll do the same thing. Now we will calculate how much time 5 is going to take to basically get the signal from 2. So this will be taking the time that 3 is basically 3 is this middle node from source node to 5. So this this was taking the time 1, and then from 3 to 5 it takes the time 3, so 3 plus 1, that is 4. Now this takes to reach 1, we took 1 second. To reach 4, we took 1 plus 1, 2 seconds. To reach 5, we took 3 plus 1, 4 seconds. So what is our answer? Our answer is going to be 4, because that's the minimum time it will take to receive the signal from 2. Okay, so this is the maximum of all this minimum distance that we found out from the source node. So basically you can see directly this will utilize the Dijkstra algorithm. We have studied Dijkstra algorithm in detail. I've written the pseudocode, and I've been basically using it in multiple problems. So check out this link right on the top to basically revise your Dijkstra algorithm. I've created like this super simple video for you guys, and it's a really quick video. So go through it. It will be useful for you like in a lot of problems of graph. So how are we actually going to use that Dijkstra algorithm? So we will be basically having min-heap. I'm just going to quickly tell you like what we will be doing. First, we will be creating let's call it like a graph or edges, or like, let's call it graph. So we'll have graph will be a dictionary or adjacency list that will have all the U's. So basically 2, and then 3, and then 1. So these are our nodes. Then it will have this list of neighbors. These neighbors will basically have these neighbors. Let's say 2 has a neighbor 1, and then the distance is 1. So 1, 1, that is one of the neighbors of 2. Another neighbor is 3. 3 has the distance. I'm just going to remove this for now, because that was not part of the problem. 3 has the distance also 1. Then 3 has the neighbor 4. So it's going to be 4, and then the distance to go from 3 to 4 is also 1. It doesn't have any neighbor. Then 1 does not have neighbor, so this is going to be empty. So that will be my graph that I will use to basically and in the beginning I will have this min-heap, and this will all, right now, if you have not studied Dijkstra algorithm, this might become complicated for you to understand. However, like if you have already checked out that link that I told you, then it's going to be super easy for you. So initially we'll be adding our source node, which is going to be k, and the distance to itself of k is going to be 0. So this is going to be my min-heap, and then I will have my while loop while min-heap as something, pop the element, and then work with that node, visit all its neighbors, and then perform the relaxation, calculating the distance. And then initially I will have my distance array that will or I'll just call it like node array does dictionary, and the dictionary will have all the nodes 1, 2, and 3. So right now initially we can say whatever my k is 2, so 2 has the distance 0, but then 1 we will be initially assigning it infinity, and then infinity will be updated later when we actually visit those nodes. Then we'll also have visit set. If we have already visited that node, then we are not going to get into the loop. So I think the core of this problem is a Dijkstra algorithm. Please check it out, and then it's going to be super easy. It's not just this problem that's going to be easy for you, like it's going to be like tons and tons of problem that will become super simple. But once you learn that Dijkstra algorithm core, then all these problems will be a piece of cake. Whatever, shortest path, network delay, this path to reach from this right top grid to the bottom grid, and then there's these obstacles. Whatever, like there are a lot of problems. I've not done all, but we're going to do. So as I said, let's create our graph. Graph will be let me first have this graph. I'm going to create this as collections dot default dict, and it's going to be a list. Okay, so now let's visit times. So for times has 3 values, u, v, and w. So u is the source node, v is the destination node, w is the weight. In times, now my graph is going to store basically it's going to store u will be the key, and then we will be appending, because the whole point of having it of type list is so that it can store list as the values. So I can directly append, and this default dict basically takes care of if that key is present or not present. It takes care of that. So that's the ease of using that. So I don't know how this became neighbor. This was graph. Maybe I had some other values copied. So what are we appending? We are appending the v vertex and the weight. All right, now let's also have this visit set. Before visit set, let's have our destination distance array. I'm just going to call it dist, not array, let's call it dictionary, that is going to have all the nodes. Right now it's going to have all the nodes, the distance from source node, which is k, all of them are going to have a distance of infinity. So let's assign the value float infinity for I in range. What is the range? N. And initially, because for the source node, which is k is going to have the distance or time to reach itself, to send the signal to itself, is going to be 0. That's it. Now let's also have a visit set. Visit set is going to be empty in the beginning, and then also have, like, let's have our min heap. That's our priority queue. Priority queue initially, let's insert the distance 0 of k to itself. All right, because this is basically the key. You will know what I'm talking about, like when I'm saying key and this is a node. If you go check out the Dijkstra algorithm video, please check out. I put effort into it. I wouldn't if it was not that useful. Now let's start our BFS, breadth first search. So while my min heap is not empty, so what I want to do now is pop the element, the most prioritized element, or the minimum distance element or node, to basically visit all its neighbors. So I'm going to call it like, let's say initially there is a distance, so I'm going to call it current time. In this case it's time because we're sending signal, so current time. And then I'm going to call it current node, so current node, and I'm popping it out from heap q. First we are heapifying, so heap q, heap pop from min heap. Min heap is basically a 2D array, or just you can call it simple array. So I'm sending that in here, and then will be giving me the current time for that current node that I'm on. That's what I need to visit. If this current node it's in visit, then I don't need to visit this anymore. It will have this distance calculated already. So what I'll do is I will continue will send me to basically to pop the next prioritized value. Otherwise I will add it to my visit, this current node, not the visit. Okay, such an idiot. Okay, now why did we pop this node? Because we want to visit its neighbors. So what I'll do is for let's call it for these neighbors, and this weight w will be coming from our graph that we created as a dictionary that has this collection of neighboring nodes for my current node, right? So I will take out from all the list of neighbors from my graph, and as a key I am sending in the current node. All right, now I have my neighbor and I have my w. So if this particular neighbor is not visited, is not in visit, if not in visit, then I'm going to calculate the distance for it, or distance node, like let's call it time. So I'm going to call the time, calculate the time it's going to have to receive the signal. So it's going to be the current time that its parent node has taken already, plus its own cost, which is w, to get to it from that source node, which is coming from the graph. I'm going to add that w. So that is the total time. Now this time I will basically update it into this distance. Okay, so if this time that I just calculated is less than, I'm trying to find the shortest time, not the greatest time or already calculated time, the shortest time or the smallest time. If this time is smaller than the time that's already present for this neighbor in the distance, dictionary. If this is the case, then for my distance, and for this neighbor, I will update it with time. Okay, that's one thing. That's one of the things that I want to update, that distance basically for each node, because it's a dictionary. For each node there is a particular value, which is the time it's going to take from the source node to get to it, like from visiting through all the paths. That's the whole core of Dijkstra algorithm. But there is one more thing. If this is not in visit, then I want to push it now, because I've already calculated the time for it. I want to push it to my heap, right? I want to push it to my heap. So what I'll do is I'm going to copy this and heap push. So this is heap pop. I'm going to heap push to my min heap. What am I pushing? I am pushing this time that I just calculated, and also basically also my neighbor, because I'm visiting it, also my neighbor. And that is it. Finally I will have this distance array that will have all the distance calculated, or basically the time calculated. I should have called it time, but like the distance is convention which I have created for myself in the Dijkstra video. So I'm just gonna call it that. So return maximum of, so that will have the values of for all the nodes, the time for all the node it has taken to receive the signal from the source node. Okay, so that's just like calculating a single the shortest path from the source node. So in this case it's this time that it has taken to receive that signal. So that will be the maximum of this dist. Remember, dist is the dictionary. I'm trying to get all its values. So maximum of all its values. Okay, that's how we receive all the values, maximum of all the values. If you have visited all the nodes, if the whole graph was connected and every node was reachable from the source node, because in some cases it might not be. So in that case, like I will return -1. So if this n is equals to length of my visit set, then I will return the maximum of these distance values, else I will return -1. All right, so I hope everything was all right. I'm gonna zoom out and then run this code. So you can see the entire code. Let's run it. Awesome. Wow. I'm going to submit it. It doesn't happen like in the first go you are able to get it accepted, and everything went really fine. Now let's write down the time complexity for this. Time complexity. Okay. Oh no. Time complexity for this is going to be, so we are visiting all the nodes and we are using all the edges. So vertices we can call it V, and then edges we can call it E. So usually the time complexity is going to be E plus V, where E are the edges and then V are all the vertices. We are visiting all the vertices and using basically those edges to go to the other vertices, and it's a BFS. So I'm just saying we are visiting all the nodes and also working with the edges because of this neighbor array. So that's one thing. Into log n. Why this log n? Because for all the nodes, or I can call it log v, why this v? That's because, or I think I will call it n, because n is the total number of vertices. I could call this also n. I don't know why I keep switching, but I think that v makes more sense. But this is because we have this min heap, and to basically heap pop is a constant time operation, but when we are doing heap push, then we are heapifying. It heapifies our basically this array that initially we created, this min heap, and then that's it takes the time complexity of log n. You can check out my another video on top right here, that is on min heap, priority queues, BFS and DFS. And for space complexity, we can just say it's going to be of E plus V. So edges and vertices that we are storing into my graph. Okay, that's it. Let's go back to AlgoYogi and mark this problem solved. See you guys later in the next problem. Until then, bye bye.